Bismillahirrahmanirrahim. Let's start the next topic on advanced operating system, which is the embedded operating system. Okay, so in this chapter, we are going to learn what is embedded system and what is the characteristic of an embedded OS, how to adopt an existing commercial operating system, or we can also use develop our own, so purpose-built embedded operating system. Okay, the next topic is on the embedded Linux. The kernel size, of course, will be smaller, and then how to compile the file system specific for embedded system, the advantage, and Android, which is one of the example of embedded Linux. Okay, we move on also to the TinyOS, which normally used in wireless sensor network. Okay, let's discuss the goals, the components, scheduler, the example configuration using the graph and the program, and the resource interface. So the learning objective for this chapter is to explain the concept of embedded system, understand the characteristic of embedded OS, and explain the distinction, what's the difference between Linux, the full Linux, and the embedded Linux. Okay, and describe the architecture and key features of TinyOS. Okay, so the first one we are going to discuss on embedded system. Okay, so the definitions of embedded system, it is a specialized device with electronics and software designed for specific function. Okay, so specialized device with specific electronics and software designed for specific function. Okay, and it's different from the general purpose computers. And the average system has been there. We have around 10 of billion of microcontrollers annually, surpassing general purpose computers in prevalence. So for example, here in the consumer electronics, we have embedded systems, smartphones, cameras, appliances, washing machine, microwave, automotive system, automatic braking system, cruise control, tire pressure monitors, and industrial sensors and control. Okay. So the embedded system normally coupled with the environment, so often tightly integrated with the environment. So that's why leading to a real-time constraint based on the precision, timing, and simultaneous activity management. Okay, so we are going to see that in the future, the integration of embedded system in future oriented device is expected to become universal. So that's why we have the hardware embedded system, and then which contain also the software, and one of the important software is on embedded operating system. Okay, so let's move on. This is the possible organization of embedded system. We have the processors, custom logic, memory. We have diagnosis port as the input or output. We have the human interface. We have the LCD monitor or LED, for example. Okay, and we have sensor. Need to have the AD conversion or actuators, the output. Okay. So the unique characteristic of any system, it includes interface for sensing and interacting with the environment, which is sensor and actuators, often forming a reactive system driven by environmental conditions. So sense the temperature, for example, and we have the thermostat as the actuators. Okay. So the human interface, this part, it's range from simple like flashing light, LED to advanced for robotic visions. Okay, and many systems also like human interaction. So that's why we put here dot 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 here, because not all will have a human interface, because once we put on a system, it will work without the intervention from the user. Okay. So it also incorporate diagnosis port for system diagnosis and special purpose hardware, FPGA like this one, the custom logic, okay, to enhance performance and reliability. Okay. The software is application specific, so that's why very specific application, often with what is the application with fixed function. There's no addition of the function, which prioritize the energy efficiency in energy, code size, execution time, the weight, dimension, and cost. So this is if we don't have some many function, for example, we don't need to have so many RAM and or memory and it will reduce the cost or reduce the weight and dimension at least. Okay. And then the modern terms, field upgradability. It is, for example, you can update the firmware on any embedded OS, okay, to improve the security, fixing bugs, errors, adding new features, and so on. Okay, and as of now, the embedded platform support diverse applications, something like smartphone and smart TV. Okay, so this is the difference between the application processors and a dedicated processor. Okay, so application processor is normally a general purpose processor which can run a complex operating system like Linux, Android, Chrome OS. Okay, so designed to support multiple apps that can run at once and handle diverse functions. Okay, and commonly used in devices like smartphone for versatile functionality. The dedicated processor is tailored or designed or produced for a specific task, okay, or a small which contains small set of function in the host device, okay. This also engineered or designed for optimized size and cost, okay, and primarily used in embedded system performing single purpose tasks efficiently. So it is very efficient to when performing only one task, okay. Okay, so let's move on to microprocessors. So you can see here, this is the simplified view of major elements on a multi-core computers. We have motherboard. Motherboard has main memory. It has the processor, I/O chip. This is also based on the von Neumann architecture, which we have cores, we have memory, we have system bus, and we have the I/O. Okay. And then we on the processor also it has some cores, multi-cores, L1, L2, L3 cache. Okay. And then each core has its own instruction logic, arithmetic and logic unit, load and store logic, L1 and L2 cache. Okay. So as you can see, this is 8 cores, for example, which has L1 and L2, and L3 it can be shared among the cores. Okay. So the processors miniaturized into one of few integrated circuit containing this one registers, ALUs, and control units. And the advanced chip can contain multi-core with cache memory. The motherboard normally in more than one layer, multiple layers. It connects essential components, motherboard, system I/O, and memory. Okay, and we have expansion slot which can allow additional components using PCIe, for example. Okay, so you can add GPU, you can add the sound card and so on. Okay. Okay, so then when we go uh, on the IC part, is fabricated on semiconductor materials and it contains 1,200 or millions of transistors. Even the CPU can contain the billions of transistors. The application, smartphone, tablet, PC workstation, and so on. Okay. Okay, for microcontroller, as you can see, it's this is the typical microcontroller chip elements. It contains the processor, RAM on the chip itself, ROM for program and data. This is for temporary data. EEPROM for permanent data. Okay, this is for program and data. So this is for permanent data. Timer. We have the clock function. We have parallel I/O, peripheral interface, serial I/O. We have ADC and DAC, okay, for as input and output to sensors and to actuator. So this is a typical microcontroller chip elements. As you can see here, you have several examples of a microcontroller. Okay, and this is optimized for energy efficiency and use minimal silicon area. As you can see here, this very small. Okay, the application on toys, appliance, vehicles, automation systems, and so on. Okay, so for example, controlling fans or machinery with simple reaction to input. The characteristics, it is a dedicated processor, so typically like human interactions. So as you can see from here, it was not designed, for example, for LCD. Okay, you need to have the expansion for LCD. Okay, It's operating architecture ranging from 4 bit to 32 bits, okay, and slower than microprocessor in the range of megahertz. Okay, this and we can found this on industrial automations and vehicles. Okay, so as you can see from here, vehicles contain around 70 plus microcontroller for various subsystems. So even in a car, you have around more than 70 microcontrollers, okay, being used. Okay, now let's see. We have the deeply embedded system. This is the system with limited programmability using microcontroller, often with logic or program burned into ROM, and there is no user interaction. Because of that, it's difficult to observe or modify behavior for both programmers and user. You need to um, take the chip or program the chip and reprogram. Okay, for example, this one is conveyor belts, okay, or robotic arms in the application. One is program, packet, and you normally it's difficult to upgrade, okay, because it's limited. It's very good for specific tasks. Okay, the purpose is dedicated to single specific tasks like detecting environments data or as a sensors, wireless sensor for basic processings, conveyor belt moving. This is the uh, electronic control unit in a car. Okay, this one is the insulation pump, and this is the digital thermostat as an example. Okay, so you can see here various applications, and the characteristic is extreme resource constraint. We have limited memory, processor power, time, and energy consumption. Often include wireless capabilities for network configuration, for example, in wireless sensor network. Okay, and it's very significant because the sense is ubiquitous, low power, and specialized application. These are the examples of deeply embedded system. Okay, so you can see from here, it can be used in industrial applications, automated conveyor belt, robotic arms. It can be used on automotive system like ECU, ABS, and TPMS. Okay, it can be used for healthcare device, implantable cardioverter, defibrillator for monitor and regulate heart rhythms, or you have infusion pumps, okay, deliver medication or nutrients, okay. And we have also any consumer electronics like our microwave, digital thermostat, and smart lock, okay, like this, okay. We has been used also in flight control system and satellite controllers, and on IoT device for monitoring sensor, agriculture sensors, and smart lighting system. Okay, so you can see it has some software specifically used for embedded system, and this is the deeply embedded system. Okay, now let's move on to the characteristic of embedded OS. So the character of embedded OS, we have seven. The first one is real-time operations. So ensure tasks are completed with the strict timing constraint dictated by I/O and control stability requirements. Okay. Second one, it has reactive operation. It responds to external events and which is often unpredictable, so requiring worst case planning, worst case scenario, and execution priority management. Okay. The next characteristic is configurability. So highly adaptable to diverse hardware and application needs using selective OS module loading and or object-oriented structure. So you can plug and play. You can configure for various application and various hardware. Okay. It also has I/O device flexibilities. Okay, so it's focused on supporting only relevant device. Okay, for example, slow device handled using the special task instead of a kernel. So you just use the special task instead of use it in kernel. So the OS will be smaller. Okay, the OS size will be smaller. Okay, streamline protection mechanism. What does it mean is it has a minimal memory and I/O protections. Okay, it's very minimum. Okay, number six is direct use of interrupts. The task can be directly start or stopped by interrupts. Okay, the last one is efficient design. Okay, tailored to constrain memory space, power consumption, and processing need, unlike full OS. Okay. So, how do we program the embedded OS? How we program the embedded system? We have the host and target environment. Normally, you doing the programming here, and then target for specific device. Like this is, for example, smart camera. Okay, that contain kernel, root file system, and bootloader. Okay, and of course, here you need to has cross-platform development environment, similar like when you are developing Android apps, you develop in the PC and then you install it the app on Android smartphone. Okay. So the host platform is where embedded Linux normally is on Linux, but there is also Windows, embedded Windows. Okay, is compiled or configured. The target platform is where the compiled configured software is executed. This one can be this is the embedded system. So the key command transfer is the bootloader, the kernel, and the root file systems, which provide only the essential libraries, not all. Okay, the application itself and configuration file for the embedded system. Okay, so in this case, we have separation of development and execution. Okay, of course, when you do the simulation here, you sometimes you have also emulator. Okay, to emulate how it's run on the target platform. Okay. Okay, so the bootloaders, so we have bootloader, root file system, and kernel. Okay, that will be transferred to the embedded system. The function is to initialize the system and load the OS kernel into RAM. We have two-stage bootloader. The first one run from ROM, load from internal flash, SD card, and serial I/O. Second one, load kernel and root file system from flash to RAM, and compress file into binary image and pass control to the kernel. Okay, the first state loader provide by processor vendor normally, or the one that develop the microcontroller. Okay, second state loader often use the open source solution, which is normally the embedded Linux. Okay. So the kernel, this is the kernel compilation. We have the kernel source from open source hardware vendor, and we have kernel configuration. We need to configure, define according to the target hardware. Okay, because we want to minimize the size. Okay. After that, we do the cross compilers that make the software executable on the host system. Then we produce a kernel image. Okay, so this is executable on target system, ready to be started by bootloader on target system. Okay. So the kernel components contain memory management, process thread management, inter-process communication, device driver, file system, networking, power management. Okay, so you can choose also from here the modules. You can select the modules or that only the required module that you can compile together. Okay, yeah. As I mentioned earlier, you can do the customization. You can strip optional component based on hardware limitation and use case. Okay, so for example, remember that paging and segmentation need to be supported by the processor. If the processor does not support it, then we can exclude the paging and segmentation. Okay. So the cross compilation is the kernel and software for embedded system are compiled on a host platform and executed on target platform, as we mentioned it here earlier. Okay. So we have the cross compiler. Okay, so let's move on. Yeah, this is the cross compiler. This is the software tools, the key features, the host system, and then we have the target system. It support development for diverse architectures. So you have uh, many example of cross compilers. Okay, so for example, you have the GCC, CLangs, LLVM, Min, GW, Code Sorcery, KL, MDK ARM, I, IAR embedded workbench. Okay, so this is the example of cross compiler. You can compile on the host on your PC, and then you can run it on the target system. Okay, so that is the kernel. Okay, now bootloader kernel, and then let's see the root file system. Normally you have a single global hierarchy. This is similar like in Linux. You have the slash. Okay, this is the root directory. You have also minimal configuration, only essential application libraries and files required for the system to function. That is loaded there. So optimized to meet the constraint need. The purpose is to provide a base environment for the OS and application to run. Okay, and the smallest Linux you can try is Alpine Linux. Is the size around on the order of 100 kilobyte. Okay. So this is similar like in the server or workstation, but with minimal components. So as I mentioned, it's similar. So you can see here, this is slash is the root, and you have slash bin, slash lib, slash etc, slash dev, exactly like a Linux file system or Unix file system. Okay. So how to develop an embedded OS? You can take an existing OS, strip it down, and adapt it for the embedded application, or you design and implement an OS intended solely for embedded use. Okay, so you have this with the pros con. Okay, so the if you adapt an existing commercial OS, the you need to modify commercial OS, some like Linux, FreeBSD, or Windows. You need to add this capability, real-time capability, streamline operation, application-specific functionality. Okay. The advantage is familiar interface, which facilitates portability and ease of use. Okay, and reduce development effort by leveraging existing OS infrastructure. But normally, yeah, it's not optimized. So this is one of the disadvantages. It's not optimized for real-time embedded environments. It is slower and less predictable performance. Requires significant modification. Okay, so although it say that we are familiar, but still, if you want to target very small embedded system that has a limitation, it requires significant modification. Okay, and also the general purpose OS focus on average case rather than the worst case. So we need to on the embedded OS we need to make it a worst case. Okay, and typically lacks semantic awareness of specific application need. Okay, the use case. This is for example for flexibility, extensively familiarity, like for smartphone and consumer device. You can see that we have the like Windows OS embedded as has been used for ATM machines and so on. Okay, or in the display panels. Okay, for advertisements they use the Windows. Okay, for purpose-built embedded OS, the objective like eCOS and TinyOS are designed to meet stringent timing and resource constraint. So this ideal for high performance and real-time reliability. Okay, the design consideration for the complex system is predictability over speed. So we need to prioritize consistent and deterministic operation. Once it's the input is specific, so you need to be able to have the same output. Okay, so that's why it should be deterministic. Okay. Okay, the second one, tailored task scheduling approach for critical time constraint. Okay. Okay, so the key characteristic of purpose-built embedded OS is optimized for real-time embedded requirements. So that's why it will be fast, real-time scheduling policies, and will be efficient performance, small size with very good response time. Okay, interrupt disabling minimize to maintain responsiveness. Okay, and we have the memory managements. We are using the fixed or variable size partition, so we don't use paging, so it's fixed size, or you can also have variable, but it will not change. Okay, so the old technique is being used for the embedded OS because it does not have the features for paging and segmentation. Okay, for the microcontroller of embedded OS. Okay, but it has also the ability to lock critical and code data in memory, still have some kind of protection. Okay. Special features, we are using sequential file for high-speed data accumulations, and it also has bounded execution time for primitive to ensure deterministic behavior. So if it's on, so you have the bounded execution time within 1 second should finish, within 100 milliseconds should finish, and so on. Okay, and it has also real-time capabilities. Okay, so this is the key characteristic of purpose-built embedded OS. Okay. Okay, now let's move on to the next topic, which is the embedded Linux. So the embedded Linux is a Linux version tailored for embedded system. So the difference with the desktop or server Linux is custom built configuration is optimized, okay, for resource constraints because you have limited memory, limited features of the processors and so on. Okay, and it has specialized development framework for embedded environments. The key features for embedded Linux is designed for efficiency in terms of memory, the usage of memory, the power use, and the processing requirement. okay, and support a wide variety of hardware platform. You just need to use different module for different device, okay, and often configure for real-time capabilities and small storage footprint. Okay, so this is the key features of embedded Linux. Okay, this is an example. There are many example. We have here around 10. Sorry, 12. Okay, we have here around 12. We have Yocto project, build root, open embedded, Ubuntu Core, Android, Alpine Linux. As I mentioned here, this is like in 100 kilobytes. It can be used in the Docker or container. Raspbian, Micro C Linux. We will discuss also this one in this chapter. Okay, TimeSys Linux Link, Tizen from Samsung. Okay, Peta Linux and Wind River Linux. Okay, so you can see that we have several embedded Linux examples. Okay. The key characteristic of embedded Linux system is the custom kernel size. Okay, so this type because this is tailored for specific hardware and purpose. So you can plug in, what you call, you can add or you can remove. Okay, so support only the device, peripherals, and protocol required. If you don't use TCP/IP because there's no networking, so you remove that one. Okay, this is smaller than standard Linux kernels do the configurability. The memory size categories on the small system, we have 2 megabyte of ROM, 4 megabyte of RAM. This is for low power processor. Medium system, we have 32 megabyte ROM, 64 megabyte RAM. Okay, medium power processor. Okay, and this large system, powerful processor with substantial RAM and storage, something like a Raspberry Pi or Arduino. Okay. So on the memory constraint and the kernel adaptation, so you can see here we have a limited memory. Okay, so this is the size of Linux kernel. This general Linux kernel, okay, in megabytes up to 2016. The Linux kernel itself now is around on 2016 125 something. Okay, 120 or 130 megabytes. Okay. So for the consideration for RAM and ROM consideration, Linux must fit entirely into RAM and ROM. Okay, so full feature kernel are not feasible. Okay, and this is the kernel growth. So we need to configure the kernels, the components removed to meet size constraint, and it ensure performance and fits within the hardware limits. Okay. So other constraint of the embedded Linux is time constraint. We have the stringent or mild time constraint. Network abilities, almost all, but not all. Embedded system support networking, mostly wireless. This is to form a wireless sensor network. Okay. User interaction, there are several types. It can be high for interactive system. It can be low as like LED or button industrial control, or none like autonomous system for IoT, like in the ECU in the automotive system, you don't have a user interaction. Okay, yeah. So you can see here, this is the table character or example of embedded Linux system. So this is the type, the descriptions, and the size, the time constraint, networkability, and degree of user interaction. Okay, so you can see the example from this table. Okay. Okay, for file system, the last one is file system on. So we have for person storage. Okay, normally we use flash memory. The internal disks are uncommon, normally not common. Okay, so the file system must be compact to fit on embedded constraints. So we have several type of file system for embedded Linux: CRAM file system, Squash file system, GFFS2 file system, UBF file system, YAF file system 2, and so on. Okay, so we have an example with the pros and cons for the embedded Linux file system. Okay, so the advantage of an embedded Linux is vendor independence, so freedom from line of specific vendors, because you can modify, because it's open source, you can modify, you can add. Okay, extensive hardware support, cost efficiency is low development and training costs, and open source benefit. Okay, so this is the four advantage of embedded Linux. Okay. Okay, for specific on embedded Linux, we have microcontroller Linux, micro C Linux. Okay, the purpose is streamline open in the kernel variant design for microcontroller and small embedded system. Okay, so it's the design philosophy is to slim down the operating environment by removing. So most probably you have because the kernel is big, so you just remove the one that you don't need. For example, unnecessary utilities, tools, and service that you don't need, you remove it. Okay, the bootable image size as small as 0.5 megabyte. It's very small. Okay, in the 100 kilobytes. Alpine Linux also can reach on 100 kilobytes. Okay. The practical configuration with Ethernet, TCP/IP, and basic tools, 1.5 to 2 megabytes, still very small. Okay. So the runtime RAM requirements, it can operate with the 8 to 32 megabyte of RAM. Remember that our general purpose computer now has 8 gigabytes, 32 gigabytes, 64 gigabyte. You can see, imagine this one can run on 8 to 32 megabyte RAM only. Okay. For example, here the M-Crack system using the Cortex-M microcontroller ARM, okay, that use the micro C Linux. Okay, this is the comparison for between micro C Linux and full Linux. Target use case, of course, full Linux multi-user. This one for embedded system. Memory management, this is support virtual memory, okay, with the swapping virtual address and so on. This one is no virtual memory because a single shared address space for all process, and we'll discuss more this on the next slide. Address handling using virtual address space is recovered on context switching. Here, applications are linked to absolute address. Okay, so if you have the address, the application on 1000 location, it will stay on 1000 location. Okay. Process creation is support fork and only support vfork. Okay, suspending the parent process temporarily. So only one process at a time can run. Okay, can create a new process, but only one process can run at a time. Okay, device drivers is use ICA or PCI for device driver. This is modified device driver to use the local system bus. On the feature of interactive user support, designed for multi-user, multitask environment. So this is designed for single-purpose embedded application. Okay. Now let's see on the memory management of micro C Linux with full Linux. Um, Process in microselect requires contiguous memory, potentially leading to fragmentation. If you remember the fragmentation, so need contiguous memory because we don't have the paging and segmentation. Okay, we don't have the page table, and also it's not paging is not supported by the limited microcontroller. Okay, so we use require the contiguous memory. Okay. So normally use the fixed set of process at boot. So you just put the number of process, 3 process, that's enough. Okay. No dynamic memory expansions. Uh, no dynamic application stack. Okay, risk stack overflow. This is used if you are doing the function call, for example, and no memory protection. As I mentioned, we don't have the process is limited, but some of the some fixes exist. For example, the Cortex M3, M4 MPU use memory protection unit. Okay, not the MMU in the general processor. You have memory management unit in the embedded system here on Cortex ARM processor. You have memory protection unit. It implement basic process and kernel memory protection. Okay. Okay, so this is the micro C Linux or micro C lib micro controller libc software architecture. Libc is the lib C library. Okay, so we have here the application. We have system call, a kernel called the kernels. Okay, and or we can use the function call to the library. Okay, and here we have inter-process communication manager, network interface, I/O interface, virtual file system, Linux memory managers, and Linux process scheduler. Okay. Yeah. So the aim for micro C lib, as the name implies, is the smaller version of the libc smaller C library. Okay, this is small C library suitable for embedded Linux environments. Okay, this is smaller than GNU C. So the porting applications from glibc to micro C libc is just recompiling the source code. So you just recompile the source code, then uh, you can have your application. Okay, it's as simple as that. Okay, as you can see here, this is the difference. Glib size. Okay, and this is micro C lib size. 1.2 megabyte. This is 284 kilobyte. 92 kilobyte, 20 kilobyte. Okay, this is for encryption, for example. This one libd, this one libdl. Yeah, sorry, libdl here, libdl. Okay, 12 kilo, 12 kilo, similar. Okay, libm format 136 kilo. This is 8 kilo. Okay, so very small. Okay, uh, the C library, micro C library support shared library and tradings. Okay, achieve space saving by disabling non-essential features by default and using aggressive code optimization. Okay, so the compilation maybe take longer because you want to optimize the code to fit on the small size of memory. Okay, so you can see the advantage, space saving, and suitable for lightweight and efficient embedded Linux application. Okay, and as an example, is Android. Okay, because this is based on Linux kernel. Of course, there are definition whether Android is there's a debate on definition whether Android is embedded Linux or not, because it support dynamic application environments. Okay, and platform Android acts as a platform OS rather than the fixed functionality. Okay, so you can add more application, different application, and Android also has vertically integrated system. Okay, in the semantic perspective, whether Android qualifies as embedded Linux depend on definition and interpretation of embedded Linux itself. Okay. Okay, so the last part for this chapter is on the TinyOS. Okay. So the tiniest is even smaller than the micro C Linux. Okay, this highly minimal OS requiring only 400 bytes of code and data memory. So optimized for small embedded system. Okay, the unique characteristic, but this is not a real-time OS due to typical workload in wireless sensor network. There's no kernel process or built-in memory allocation system. This is a component-based architecture with non-blocking operation. Okay, you don't check. Okay, you don't have blocking operation. You just when you execute, you don't check whether it's acknowledged or not. Okay, to minimize the design. Okay, peripheral dependent interrupt handling. So designed for low power consumption and simple application, normally it's implemented on the wireless sensor network and off most of the time with minimal processor contention or processor usage. Okay, so by default, wireless sensor network will be off most of the time. Or at the moment that periodically, then it will waking up and send the data or calculate the data, for example. Okay. Okay, so let's move on. This supported by 500 plus organization. So this is the typical wireless sensor network topology. You have the sensor. This is sensor also and relay. This is the base station, sensor and relay. The leftmost is sensor. So the rightmost, and then you have sensor and relay. Okay, you have wired link here, but the rest is wireless link. Okay, base station, and you have host PC. Okay. So the complex sensor with logic can now fit into a cubic millimeter. So very small, this size maybe millimeter size. Okay, it has the sensor and also it has the logic. Okay, the application of WSN is low cost small size sensor used for diverse application for environmental monitoring, healthcare, and industrial automation. Okay, so the system configuration you can see in this figure, you have base station and you have sensor and you have also, you can transfer directly to the base station or you can, if it is too far, then you can use a relay node. So the measurement from here can hop to here and then can reach the base station and then record it on the host PC. Okay, so the network requirement is ad hoc network capable which capable for rapid and large scale deployment. Okay, and also support for self-assembly and the configuration to handle mobility, RF interference, and dynamic environment. So maybe this one will change. Okay, if there's too many interference, maybe you cut this one and you can have, or if you have add this one, you can add to here to here. You can measure the RF interference or the distance. Okay, then it can manage itself. Okay. So the TinyOS goals, we have six goal. The first one is high concurrencies, designed for concurrency intensive. Many things run at once. Okay, application in wireless sensor network. because you can sense many things, many sensors at once. Okay. Resource efficiency, because it has limited memory, component resource, and power. Hardware adaptability, but should be portable across evolving hardware with minimal software change. Okay. Application versatility, it can support diverse applications. Platform diversity, it can design for compatibility with a wide range of platform to enhance usability. And the last one is robustness, with for long-term unattended operations. Once you deploy, then it will run for years. Okay. So another not goal, another objective is to minimize the buffering. Okay, so we just focus on capturing, processing, and streaming data in real time to reduce latencies. Okay. The TinyOS component, we have five modular architectures. It's built from small specialized components that perform simple tasks. So components have limited, well-defined interface with each other and hardware. Okay, so there's no kernel. This lacks a traditional OS kernel, like instead of components and lightweight scheduler. So you have only components, you build components, connected various components, and then after that you just use the dispatcher or scheduler, okay, run the components. Okay, it has standardized components. Okay, for example, open source module for Commonwealth sensor network, like single hop networking, ad hoc routing, power management. It has timers component and non-volatile storage control. Okay, and also it's we can use custom configuration. The user can add application specific components. You can build different components for different application. Okay. And also simplified integration. So TinyOS act as flexible suite of components rather than a traditional monolithic OS. Okay. The final implementation of the apps consists of selected, standardized, and user-defined components. Okay, so you can have the standardized component, and you can have also user-defined components. Then you connect. It's like a function. Okay, input, output, and then you connect and so on. Okay, so this is the TinyOS component. For example, this is timer M component. This is the block diagram. You have the input. Okay, and then you have also the output. Okay, you have here also the input, and you have also the output. Okay, so you can connect input and output. Okay, this is the module timer M. Okay, this one. Okay, this provide interface standard control, timer, and use interface clock here. Okay. Yeah, so the TinyOS consists of small modular component, each performing specific tasks. As mentioned earlier, the specific task in here will be timer. Okay, this timer is providing the timer, clock, and standard control interface for real time, for time-based operation. Okay, anything with time, then it will use timer. Okay, so the interface include start, stop, and also events like fire. Okay, start the events. Okay, there's no kernel, only relying on the standardized component and lightweight schedulers, as we mentioned earlier. So the task and event model, the tasks in the TinyOS are atomic, mean once it's run, it cannot be stopped. Cannot be stopped. Okay, non-preemptible means that it cannot stop. Okay, and other process cannot stop the task. Okay, and run to completion. So this is the basic of atomic. Okay. But the task also can schedule other tasks, issue comments, or signal some events. Okay, we have tasks and we have comments. Comments are non-blocking and initiate action in lower level components. Okay, and the last one is events. It notify components of task completion or hardware interrupt. Okay, so you have the tasks, the comments, and the events. Okay. So for the hierarchy architecture, normally you have application component at the top and hardware components at the bottom. Okay, so this is the hierarchical architecture. Okay. Okay, for component wiring, we can see here the TinyOS components are connected through interface. So for example, like here, timer. Okay, you have here the input. Okay, and you have here the hardware. So you can connect to that. Okay. So this is the implementation of component and configuration. This component, and then we have configuration. Okay, so configuration define how components interact by wiring their interface. You can see this is the implementation. Okay, the configuration. Okay, component is timer M and hardware clock, standard control, timer M, standard control, connect to this. Timer M, timer, connect to this. Okay, timer clock is used the hardware clock. Okay, so as mentioned earlier, we have the application on the top and hardware components at the bottom. Okay, application on the top and hardware component on the bottom. Okay. So naming convention, timer C represent the configuration component. So this one will be timer C. Okay, yeah, you can see here timer C. Okay, represent configuration component. Module mean M, so you have module here. Okay, so the configuration allows user to interact with high-level components, timer C, without managing its internal subcomponent connection. So after you define this, then you can use this is the your input. Okay, and the output is here. Okay. So then, yeah, so this is the example of timer C. In here, we have timer C link the timer module, timer M to supporting components. You can link to the clock and LED. Okay, so this element that you need for user to wire these subcomponents directly. So this efficient modular design. Okay. The TinyOS scheduler, remember that we don't, this is the core, that's why only 400 bytes. Okay, this is the core of the OS of TinyOS. Okay, so this universal focus, only one task execute at a time. Okay, and default is first in, first out scheduler. Okay, and this is also power aware design. The schedule put the processor to sleep when the task queue is empty. So remember that you have the ready queue, or we can have put here the task queue. Okay, and then we have running on the processor. So if this is empty, then it can power down. Okay, you can put the processor to sleep. Okay, then the system will work again by the hardware events. Okay, so for ensuring efficient battery usage. Okay, we have the two scheduler generation. We have TinyOS 1.x and TinyOS 2.x. Okay. Customization, or still, although they have some default, you can customize. For example, the first in first out here scheduler can be changed with the priority based or deadline based schemes. Okay, efficiency overhead. The simple design ensure minimal overhead. This is quite crucial for embedded system with limited resources. Okay, so this very efficient of overhead. Okay, so this is an example of configuration in TinyOS. This is the search applications perform periodic sensors sampling and ad hoc multi-hop routing to transmit data to a base station. Okay, the component and software are interconnected using the interface to form the complete system. Okay, the module is you have search M. Okay, search M modules, application level component connecting the operation of the system. Yeah, this one. Okay, and we have components like ADC, timer, and send message are wired together to handle specific functionalities. Okay, this is the simplified view of search application. As we mentioned earlier, you have search M, manage the photo, timer, multi-hop, LEDs. Okay, and also send the message, queue send, and generic communication. Okay, in here you can see the details, the top level search configuration. Okay, similar like we put earlier. So from the modules, we have the components and we have the tasks, we have the events. Okay. Yeah, so this example also, then you can see the implementation of this. You can see in the C here, this is the configuration. Okay, how it's connected. Okay. So yeah, the timer initiate or timer start every seconds. The ADC read the sensor, get data, transmit via send message. Okay. We have also standardized interface like standard control, ADC, timer, send message, and LED. Okay, so this one can be replaced and can reuse. Okay, so that's the benefit. Okay. Okay, so the strength of TinyOS is highly modular and hardware software abstraction. It also offers the flexibility and scalability. Okay, as the interface, the last one, we have the resource abstraction. We have dedicated resources like interrupts and counters. We have virtualized resources, okay, like clocks and timer, and we have shared resources it can be accessed via an arbiter components. Only one client has control at a time. Okay, so the arbiter role is to manage resource access and then ensure that the client holding a resource has uninterrupted control and assume cooperative behavior. Okay, the client responsibility is to explicitly acquire and release resource as needed. So arbitrators cannot forcibly reclaim resource from clients. Okay, so it trust the client will use efficiently. Okay, so use case, for example, for simple subsystem, filters for multiplexing non-conflicting resource, and shared for critical resource which need the exclusion. Okay, so this is an example, shared resource configurations. Okay, so we have resource requested, resource configure, resource specific interface. So this is built on TinyOS. Okay, so we have arbiter and shared resource components. Okay, and the interface provided to clients is the resource interface. Okay, resource requested interface, this one. Okay, resource configure interface, this one. Okay, and resource specific interface, this one, with all the function defined here. Okay, so the workflow also shared resource access. Okay, yeah, the client requests access via the arbiter, and the arbiter logs the resource, process the request, and grant access. So, and then the client interacts with the resource through resource specific interface, this one. Okay, and the client release the resource when done, allowing other queue requests to proceed. Okay, so this is the an example of using the TinyOS. Okay, so a summary for this chapter, we have discussed the embedded system. Okay, we've discussed the specific functionality, integration of electronic and software. Also, we discussed the general application processors and dedicated processor, and we categorize microprocessor, microcontroller, and deeply embedded system. Okay, the characteristic of embedded operating system is focused on real-time reactive operations and development, including host and target. So you develop on host and then you deploy on the target. Okay, so example, purpose-built OS like eCOS or TinyOS, or you have embedded version of Linux. Okay, embedded Linux. Okay, an example of, so we have here embedded Linux and TinyOS as the example. Okay, so this is built from general purpose, then you adapted for embedded. TinyOS is designed for purposely for the embedded Linux. Okay, okay, thank you very much. Assalamualaikum warahmatullahi wabarakatuh.